Are you guys still interested in this idea of bringing in speakers and doing a panel discussion before? All right, so we're on a roll. I think we have people that are interested in coming, a number of people from UAMS, research applied to clinical, and clinical people that do research. So there's a number of different people that I've talked to. The biology department seems interested, the chemistry department seems interested, ACS student affiliate seems interested in supporting some of these, and I'm going to approach the biology student organization as well and see if they're interested. So a lot of different people will come together, make this happen. My goal is to have it start at 4 o'clock on Wednesdays. 4 or 4:30?
4:30.
Yeah, so the challenge is, I guess we'll do an hour and a half, so 4:30 should work. And I'm trying to find funding for food, because I'm sure, like me, you guys are always struggling to eat before class, and especially if you have lab afterwards, it's tough. So I can't promise it'll be great food, or that the university will approve of the food I get. But that will be a goal of mine to try to get. So just know that it is in the works. It might be another week or two until it gets up and running. I will open it up to the university, but my primary focus is to have you guys get that opportunity. So hopefully it'll align with what you're able to do. Yeah, Aaron?
You want me to see if my restaurant will donate food?
If who?
You want me to see if my restaurant will donate food?
I mean, that's always amazing.
Sometimes they will.
Yeah, sure. Let's talk about that. Wow, that'd be fantastic. Thanks, Aaron. So, any other logistics I need to talk about? Supplemental instruction. We have week 2 starting tomorrow night. It's still going to be in ETAS 406. That will be activity 10 that you guys picked up today. Is it worthwhile for me to print it out for you guys?
Yes, please.
Okay. I do have it posted in Blackboard as well, but I think it costs me a lot less than it does you to print it. So I will do that going forward. The second SI session of the week, remember, is Saturday online, 2 to 3:30. And I think that the feedback I got, it was a valuable use of time. So we'll try to do the same thing and even improve it, and I should be able to join this weekend, so we have 2 facilitators there. All right, so today we are going to shore up a couple things that we didn't finish last class, but we are also going to spend some time doing what you did for your pre-class quiz, which is colligative properties. So what do you guys think? What are your answers here? Talk to your neighbor. Based on your answers, you guys don't have a solid foundation in this question. Does that seem right? So maybe we start out, what's a colligative property? How does that sound? Sarah, what's a colligative property? No. What is a colligative property? That's what might influence it, right? So it's asking what influences it. Let's go.
It influences the decrease in vapor pressure.
Great. So decreasing of vapor pressure is one colligative property. What are the other ones? There's 3 others. Boiling point goes which way? Goes up. Maria?
Decrease in freezing point.
Freezing point goes down. And the last one, Christina? Osmotic pressure increases. Okay? So those are what we call colligative properties. So then the question is, that happens by putting a solute into a solvent, making a solution. The question is, does the number of particles we end up generating in solution, is that what decreases the freezing point the most? Is it specifically what the identity of that particle is and how many of them there are? Or is it just about the identity of them? So now that you know kind of the things we're talking about, does that change your answer? This is kind of a 2-tiered answer, but for right now, I'm just going to leave it that our answer is only the number of particles dissolved in solution. The identity of it has zero to do with how it influences those colligative properties. Zero might be, it's always hard to say absolutely zero. These influence whether it will dissolve, but if it does dissolve, this is the only thing that matters. All right, so we'll come back to that today. We'll spend a decent amount of time. So my goals for you guys today is by the end of class, you will be able to kind of do conversions between multiple concentrations. We've talked about molarity, molality, mole fraction. The bigger things I want you to be able to do are to be able to calculate changes in boiling point and freezing point are the two we're focusing on today. And we're going to be focusing on that based on the addition of a solute. The big thing that we're going to spend the first half of class on is, I think we had this last class as well, right? I want you to be able to articulate what is boiling, what is freezing, how does that change based on a solute, all from the molecular perspective. Our goal is to be able to visualize some of that. So, one of the parts of last class's in-class worksheet that we did not finish, I printed it again, so because we were going over 2 pages anyway. What I wanted you guys to start with is, how do we already have mosquitoes?
Oh, they got some temperature so that they hatch, and then now they're released.
And then it's going to freeze, it's going to kill them all.
I hope so. Once they get you, go back to brooding. It's only the female divided, but kill it.
Okay. We do a lot of observations of graphs in this class. We have you plot a lot, we have you look at a lot of graphs and try to interpret them. Take a minute and try to think about how this shows a sample of water at 300 degrees Kelvin. So try to describe your neighbor what this graph is describing. Okay, so we're going to do this in 2 parts. I heard some people talking through the second part because it's written up on the board. Part 1 was, let's orient ourselves to what that blue line is and how that represents a sample of water at 300 degrees Kelvin. Lynn, do you want to share your thoughts?
I'm sorry, my head was just still up from you talking earlier.
I appreciate that.
Phased out.
Would anyone like to volunteer to describe what your group discussed as how that represents water at 300 Kelvin? Anthony?
We were thinking it's the distribution of the water molecules' speed at 300 Kelvin. So
Great.
You have like a large majority going at this speed, and not so many going at like super fast.
So there's a majority of the molecules, or the most frequently occurring speed is somewhere around here. Are there any molecules that are standing still in this sample? Where would that be in the graph? With 0 speed. Are there any molecules moving 0? That's on purpose. I didn't mess that line up there. Yes. So the answer is yes. And this is going back to the pool ball analogy I had the other day. If you have a lot of energy and you have a bunch of molecules moving around, at some point in time you will find something that's standing still. It might just be for a fraction of a second.
I thought you said that yesterday, even under extreme lab experiments, nothing's gotten to.
The whole sample will not have 0 movement. Movement is vibration, movement is... So this is speed. Does this refer to vibration?
No.
So
tandem, right?
In what?
Tandem together. Because the speed of the structure of an ice crystal is very slow, but it's still vibrating. But
So
it still has some speed.
You could say the hertz or the frequency of it, but that's typically not described as fair enough. You could argue that that is a speed. Hertz frequency is speed. Okay, fair. In this particular graph, it's good. This is why we're all orienting, right? I appreciate it all.
I'm not trying to be a dick. That's what I.
Right now. I love Josh. He is fantastic. And he's always willing to share his opinion when we have something that I'm not very clear on. So thank you. So in this particular case here, we're talking about the speed of molecules moving. We're talking about translational motion and the speed of that motion, going from one point in space to another point in space over time. And so there are always some molecules that are not moving in a sample, regardless of how warm we make it as a liquid, but also as a gas. Are we comfortable saying this is a liquid? The sample is a liquid as a whole? How do we know it's a liquid? Or how would we argue it's not? Angel?
It says water.
Okay. True, but water can also mean H2O. Christina?
I mean, there's multiple, so some of it's liquid and some of it gas, and some of it, isn't it an average of all of them, kind of?
Okay, yes, we will get into that in 1 second. There's a little bit more nuance than this. Carol?
Because it's water at 300 Kelvin,
Okay, and what's the boiling point of water?
100 degrees Celsius.
Which is how many Kelvin? 373. Okay, so we're under the boiling point of water, so we assume the majority of the water is in liquid form. Alright, so the big question that we're now trying to address is we have, just to make sure we're all oriented, we have some molecules that are not moving any distance at all at a particular given point in time, some that are moving faster, 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 a lot that are moving at this particular speed. As we look at how many are moving at a faster speed, there's fewer, 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 and fewer. Okay? I want you in pencil, ideally first, to draw a second line representing what would it look like if we warmed it up to 350 degrees Kelvin. So with our very most simplistic view, if we warm up a sample, what happens to the speed of those molecules on average? It increases, right? So the molecules on average speed up. So what does that mean for our graph? Will someone be willing to draw theirs on here? Want to draw? You put your hand on there, it only registers the pencil.
Okay.
Okay, great. And can I have someone else who's willing to share as well? We'll do a few drawings up here. Lynn was the next person, I think, to raise her hand.
Intentional hand raising.
Okay, anyone else want to add a different line drawing up here.
It's supposed to be just as tall, by the way. Give a little hat.
Anyone else want to add one? Okay, so let's look at the red versus green. Which one of those shows an increase in average speed of the molecules?
Green.
Okay, so this one has more molecules moving at a lower speed than blue. So the red one would be appropriate if we're talking about cooling the sample down, lower average speed. The green one has a shift to the right. So at a lower speed, are there more or less molecules moving as fast at the warmer sample? There's less at this particular speed than the original sample. But if we go on the far other extreme, right, if we look at a faster speed, we have more molecules now moving at a faster speed than the original temperature. All right? One thing that I saw that was very different on some other people's was I saw that. What might be something that isn't quite accurate with that graph?
You started.
Hand raising so we can hear from different people. Yeah, Samantha?
The number of molecules goes all the way down to the bottom.
Well, so that means, where? Are you talking about here?
On the
Or here?
purple line, it like when it starts.
At this end or that end?
That.
So,
It like starts with 0 molecules at a certain speed.
at 0 speed and at a few of the smaller speeds. Great. So the big distinction here is that no matter how fast those molecules are moving, at least until we have them in gas, and even as a gas, we still have some molecules at any point in time that are standing still. So this doesn't represent that some molecules, even when you warm the water up, are still going to be found standing still. So this line needs to connect over at the origin to say that, and slightly above it, like both of these other graphs did. So there are always going to be some molecules moving at 0 speed.
With warming up the sample, does it make it less number of molecules not moving? So like more molecules are moving?
So there might be slightly fewer molecules we find that are not moving, yes. That would be I don't know how significant that proportion is, because once they're moving, there's very few that are found not moving. They might stay not moving for a smaller fraction of time, but there might be the same proportion of them. I'm not 100% sure of that. So the one last thing that I actually really liked that Lynn did that she said she didn't mean to do was she made the peak lower. Why is that important?
For the distribution. Kind of spreads a little.
Okay, so if you think about the blue graph, it says that there's a distribution of speed. Most of them are found here. But if we took the area under the curve of the blue graph, that's essentially how many molecules there are at all the different speeds. So if we kept the peak the same height, it would say that now we have a wider peak, we have a bigger area under the curve. We didn't make up molecules by heating it up, right? We just spread out the speeds they're going, and now we find more at a faster speed. So I actually really appreciate that green peak is lower. So I'm going to go ahead and see if I can... Actually, I'm just going to do this for right now. All of your dots are individual motions. Okay, so for a second now, we're going to talk about going from liquid to a gas. Remember before we talked about what keeps liquid together? What keeps liquid molecules from kind of just floating all over the place? Let's hear from different people today again. Yes. Intermolecular forces. So they're attracted to each other. So when they get to the surface, there's an intermolecular force strong enough. It'll pull it back down and it'll keep going. But once we have a certain molecular speed, let's say that molecular speed, now if a molecule comes close to the surface, it has enough speed to overcome that attractive force that would pull it down, and now it can break free. If the speed is great enough, right, it has to be going over a certain speed. So I want us then thinking about what happens when we warm the sample up. What happens to the vapor pressure? What happens to that line? So I'm going to draw the second line that Lynn drew. I don't know if I'm going to draw it quite as well as her. Maybe that wasn't great at the end there.
The dots help.
They did. And I should have used the dots. Okay, so I want you to talk to your neighbor about two things. What happens to the amount of energy required to overcome the intermolecular forces? And then what happens to the vapor pressure, both of those when you warm up the sample? Kind of trying to summarize and write it down. When we warm the sample up, what happens to the energy needed to become a gas? And what happens to the vapor pressure?
More molecules.
Scoot over and get in the conversation. Do you mind wrapping her in? Thanks. What are you guys thinking?
So does it decrease as more molecules are able to become gases?
Well, where's the vapor pressure measured?
Where's what?
The vapor pressure measured?
Barometers?
That's a type of instrument you can use. But do you measure it in the liquid or you measure it in the gas above the liquid? Okay. So then what happens is you warm it up to the portion in gas? Think about it that way.
So then what happens to the force? What happens to the
I'm working with it, but I'm
So maybe drag that line for 2 out so they don't come from here, I mean. Do you see the difference in the tail?
I didn't want to go past the line on here, but I see what you're saying.
Okay, can I get a new volunteer? What happens to the amount of energy required to overcome those intermolecular forces and become a gas when you warm up the sample? What happens to this line, which represents the amount of energy needed to overcome the intermolecular forces when they're moving past each other? So the energy, we can also talk about energy and speed kind of interchangeably. Once they have enough speed, it means they have a lot of energy. If they have a lot of energy, they have enough speed. So what happens as we heat it up? What happens to the amount of energy that each molecule needs to have when it gets to the surface, if it's actually going to break free and go from the liquid into the gas phase?
If the temperature's higher, you need less energy?
What do you guys think? Lynn, you're shaking your head. Why?
I think, doesn't the energy required to become a gas remain the same no matter what, but as the temperature changes, just more of those molecules will have that energy?
What do you guys think about that? So the ideal gas law says that if you increase the temperature, the pressure will also...
EV equals nRT.
Right. But that's in a closed system, and there's a whole bunch of other things, and so it's a bit different than going from liquid to a gas. So there's a couple different things that we might not want to overlap there. So on this graph, where would we circle the molecules at the colder temperature that have enough energy to become a gas if they're at the surface? Where would we circle those? Anyone want to describe that? Ruby? What about the orange line?
Where the orange and the blue intersect.
Okay, and I'm going to add, it's that percentage that fraction of the molecules have enough energy to overcome the intermolecular forces if they get to the surface. Logan?
So if we were to heat it up to boiling point, so 373 would the peak of the curve be on that line, since the average of them would be able to regulate?
So the peak of the curve definitely shifts way right to the point where what's interesting about this is a snapshot in time. If you come back a little bit later, you're going to have these ones are gone because they're gas, right? So you're going to have it shift a little bit over here again. And then if you come back a little later, those ones are going to be gone as a gas. It's going to shift right a little bit. You guys ever notice how when you go outside on a rainy day, how those puddles disappear? Did you boil them?
Yes.
It's because there's a certain amount of energy present. There's also a few other things to do with humidity and, ability of the air to become saturated with water, a number of other factors. But that's one of them, is that you always have a distribution, and if those molecules go away, it's actually Le Chatelier's principle. And we'll be talking about that soon when we get to equilibrium, that if you remove products, that the equilibrium between gas and liquid, if the gas keeps going away, then you're still going to have an equilibrium between gas and liquid. And if you remove that gas and it goes away, right, expands into the atmosphere, then you're going to have more of that constantly going forward. So then what part of this graph would we highlight to represent the proportion of the green molecules that can become a gas? You wanted to draw? I saw.
Okay. Dang it.
So highlight all the molecules you think from a green
I
sample.
knew it was coming. My bad if I'm wrong. Okay, that's what I put. Okay. How's that? No, yeah,
High five.
That's right.
All right. Why did you highlight those? So that is the portion of the molecules that are the green molecules at this higher temperature. A small portion of them have the speed or energy to overcome the intermolecular forces when they get to the surface. And that proportion, how does that compare to the blue sample? It's a bigger proportion. There are more molecules that are able to overcome those intermolecular forces and become a gas. So those intermolecular forces don't change the strength of the force. It doesn't change how much speed you need to overcome that force, because the forces are the same, the molecules are the same. It just says that that happens more frequently, the warmer the sample is. So your book shows this graph like this, and I think this is one of the most confusing graphs in general chemistry, because they don't talk about, this is the first one I've actually seen where it says blue and purple are the, but then why are they adding two different temperatures? And it's super confusing. So what we just did and what we talked about is explained in your book in figure 11.9. If you want to read more about it, that is a good place to go. You guys have any questions on this topic of speed and energy required to overcome intermolecular forces, to boil, or to become a vapor, I should say, to vaporize, and then how that relates. So one question I want to add on top of this. What would be different, and I think I have this written down on the paper, what would be different if we weren't looking at water? Let's go back to the image we just had. If we weren't looking at water, if we had a molecule that had slightly weaker intermolecular forces, what would be different about this graph? Talk to your neighbor. What would be different if the molecule had weaker intermolecular forces? Can I have a new volunteer for this one? And is it Colin?
Yep.
Okay.
I guess the E line would be to the left a little bit.
Why?
Less energy is required to break down the forces because they're not as strong. Break molecules, break the I guess, intermolecular forces when the molecules together.
So I might use the word overcome instead of breaking. So as the molecules are moving past each other in a liquid, if those attractive forces aren't as strong and they get to the surface, it doesn't need to be moving as fast. So that speed or the energy required, if there were weaker intermolecular forces, would be further to the left. What would that mean about, are we going to find higher or lower vapor pressure for the molecule with weaker intermolecular forces? Talk to your neighbor. And I'm going to do this as a clicker. So we're talking about the molecules with lower intermolecular forces. Are they going to have a higher or lower vapor pressure? Go ahead and make your decision, consulting with your neighbor, and then select your answer, please. Clickers are open. Let's do another 10 seconds. Clickers are open, 10 more seconds, 5 more seconds. Question is, will the vapor pressure be higher or lower if we're only comparing something with water's intermolecular forces or something with lower? So we have almost a 50-50, so let's make sure, very sure we're on the same question. If we're comparing this molecule with this molecule at the same temperature, so let's pick whichever line we want, right? If we look at the green line, are we going to have a higher vapor pressure with the black line, or are we going to have a lower vapor pressure with that? You want to try to explain your answer and why? Matthew?
Vapor pressure will be higher because there is going to be more molecules with the required energy to become a gas.
And vapor pressure is a measurement of the pressure of the vapor, right? Vapor is a gas. So if there's more molecules in the gas, you're going to have a higher vapor pressure. So I completely agree. Vapor pressure would increase with a lower intermolecular force. And this is one way to visualize why.
That should be a test question.
It sounds like a great test question. All right. And so I would advise you guys to spend some time reading over vapor pressure in your book. Figure 11.4 shows it in that part of the book. They kind of discuss it. You can say at different temperatures how much vapor pressure you have over a liquid. What happens when, if you look at one compound, right, one line, what happens to the vapor pressure as you warm up a sample? Vapor pressure goes up, right? This is our vapor pressure on the side here. Why?
More molecules could be vapors.
All right, so I want you to think about the conversation we just had, how that helps you describe what happens here. And then once we get to a certain temperature, which vapor pressure equals atmospheric pressure. You guys comfortable with millimeters of mercury? Also known as 1 atmosphere, 760 millimeters mercury. So this is 1 atmosphere if you were to use atmosphere. Once you cross that line, that's the boiling point. If you're at higher altitude and you have lower atmospheric pressure, what happens to the boiling point? The boiling point is here instead of here. So this is another way, kind of like everything fits together, you can talk about vapor pressure, intermolecular forces. You can look at the relative strength of intermolecular forces between these three lines, and you can use that to justify why the lines are shifted left to right, why you have a larger pressure above the liquid at different temperatures for different compounds. All right? So this is more practice of making sure you can fit things together. The last part is the Clausius-Clapeyron equation is based off of this idea that the pressure above a solution, what does the symbol mean? Proportional to E to the negative delta H vaporization over RT. What does that mean? How does this relate to intermolecular forces? Talk to your neighbor. Which of these on the right side of the equation changes based on intermolecular force strength? What on the right side of this equation changes based on intermolecular force strength? You compare two different molecules. Which of the factors on the right side of that equation would be different? Alright, can I hear from a new voice? How is intermolecular forces related to this equation? Specifically stuff on the right. Avery?
So the change in H, I think would change because if you have your intermolecular forces as we were just talking about in that last question, that influences your vapor pressure.
Okay, but what is delta H vaporization? What is this? What was that? It's the heat of vaporization or the change in enthalpy. Remember we looked at the heat curves? The heat curves we had solid, solid liquid, liquid, liquid to gas. What one of those lines did we refer to as the heat of vaporization? That's the enthalpy of vaporization. It's how much heat is required in order to overcome the intermolecular forces to go from a liquid to a gas. How does that change based on intermolecular forces?
Weaker intermolecular forces require less.
So if we had something that was weaker, it would have a shorter line there. Okay, so intermolecular forces play into this equation. Basically, the moral of the story is everything in chemistry fits together. There's an equation you can actually use to say that the pressure above the solution mathematically is proportional to the strength of the intermolecular forces, which can be described as how much energy is required to overcome those intermolecular forces for the heat of vaporization. The actual Clausius-Clapeyron equation is shown here. This is what most places use. So you can say, if we look at the vapor pressure at two different temperatures, how are they related? Well, at the first temperature, we can measure the pressure, and we find the temperature. We can measure the pressure at a second temperature, and then through the heat of vaporization, they're related through a logarithmic function. Remember that graph I just showed you guys? What kind of a shape is that graph? Logarithmic? Okay, so that is that equation. You can pick 2 points at different temperature, relate their pressure and temperature, and this is how they relate together. I think I have one problem on your homework this weekend where you have to use this equation. I really want you to be able to understand the concept, and doing mathematical utilization of it sometimes helps reinforce that. So you will have to do it once, I think, or at least one question is on that. But that might mean there's 3 questions on that. All right. So we've talked a lot about pure solvents. Just having one solvent, right? Either ethanol or diethyl ether, we're shown in that last graph for water. We're talking a lot about solutions in this class, though. I'm interested actually to hear your responses. Why do we care about solutions? It might be very different from different people in this class. Where are you guys experiencing solutions? Why are you required to take this class? What professions? David?
I guess like for certain concentrations of like saline, normal saline can be applied to the blood and the body so they can carry on those ions.
Yeah, if you inject pure water into someone instead of saline solution, is that good? No. No. They die. Depends on how much, but pure water is toxic to your blood because osmotic pressure, ligative property. So your red blood cells burst and you cannot deliver oxygen and you die. So that's one example. I imagine our geologists in the room could give us some other examples as well about studying solutions and what that tells us about all kinds of other things. But most of our biological applications that we're interested in are all about how things function in relation to each other. Really, all of the world around us, chemical reactions don't happen unless things collide with each other, and they collide with each other mostly in aqueous solution. So if you have two different molecules, if they don't touch each other, they're not going to have a reaction, and to allow them to move through the solution, they're going to interact with each other much more readily. So cells are all full of fluids that allow things to interact and touch and to move. You can even talk about specific concentrations and concentration gradients and how that propagates storage of energy and a ton of other things. Sarah, do you have a question? Or holding your elbow up? There's some super cool simulations or little videos they put together that are like animations of how things actually happen in the cell. So if you haven't visited this Harvard website, check it out. It'll be linked on the slides I'll post after class. So since we're talking about solutions, we're talking about things dissolving in solution. So if we look at these three different options, which of these three do you think is the most likely to be water soluble or the most water soluble?
Which one are we going with? You want the letters on here?
Are they different?
Yes. B and C are supposed to.
Let's use the letters on the screen because I flipped them. Way to be on your toes.
I actually was rude on something.
It's totally on purpose.
I'm not gonna lie, I can take it.
Sorry. Just so you all know, the letters up here are different. Let's make sure we're on the same page. Let's use these letters for clicking it in. Or we can do it as like a...
I keep forgetting what time it is. Last year, so much.
10 more seconds. All right. We have a majority answer, but not everyone on the same page, so we need to hear from a student which one and why. We have a decent number of people that are saying B. Why might we say B? Logan.
Alright, so when I looked at A, first thing I thought was ionic because of Ag being magnesium being an ion and sulfate also.
So magnesium being a metal and sulfate being a polyatomic ion. Let's be a little clearer on the terms. Okay.
Therefore, it won't be as soluble. And in C, so the only thing that could really bond with hydrogen, make hydrogen bonding and let it like blend in, it will be nitrogen, but it already has 3 bonds, so it doesn't have any pair of electrons that could do hydrogen bonding.
Does everybody agree nitrogen does not have any lone pairs? So it does have one lone pair.
Okay, it has one, but as we can see in figure B, it can bond with nearly all of the oxygen.
Bond with?
I think it intermolecular have forces between each other.
Intermolecular or interact?
Yeah, you got it.
Yes.
It's water soluble.
Okay, are there any lone pairs in molecule B? How many? Okay, if you're still not comfortable with line structures, what's implied, what's not, please come to office hours and see me. We did go over this in the last office hours, but I'm happy to help catch you up if you're not. And if you're not able to come to my office hours, send me a notice. Try to pair up with someone else so that it's not just one-on-one. I try not to do individual tutoring when there's 50 people that could use help, so I try to make those sessions more open. But we'll try to figure out a time to get you up to speed. So lots of carbons, lots of hydrogens, lots of one nitrogen, lots of oxygens, lots of lone pairs. So what do you guys think? Does everyone agree with answer B? Our answers have shifted since he made that answer and that description. Josh?
I still disagree.
Why?
Because I Googled the shape of... did. I got shape.
I'm glad you're still able to draw your Lewis structures from first semester.
I just wanted to make sure that magnesium wasn't attached to the. It was attached to the oxygen. It wasn't attached to this sulfur. So it showed oxygen with 2 double bonds on the sulfur in the middle, and then oxygen. So basically, it created almost a tetrahedral with magnesium on the outside. Which the oxygens, there's tons of double bonds there, and yeah.
Okay, so
wouldn't that gravitate towards a lot of
one thing to keep in mind with
in a simple structure
with salts is that while it just shows one of each, you never see a salt with just 2 ions together. It's always a huge amount, and that's the simplest unit of it. So that means we have sulfate magnesium, sulfate magnesium, sulfate magnesium, sulfate magnesium all the way across. And so that means that each sulfate has 1 magnesium between it, each magnesium has 1 sulfate on either side. So Manu, did you want to add to the discussion on that?
Well, since it's an ionic bond, it takes like around 6 water molecules to mass the charge. So that make it more water soluble.
Fantastic. All right, so first semester in my class, we spent a lot of time talking about if you have an attraction between an ion and a partial charge. We even talked about it at the beginning of the semester, right? What has a stronger attraction, a partial charge and a partial charge, or an ion and a partial charge? Ion has a stronger attraction. So this is going to attract stronger to water molecules, and 1 negative charge actually has to attract 6 water molecules in order to kind of mask that 1 negative, because the water is not a formal positive on the hydrogen, it's about a 1/6 of a positive charge. So we're going to surround this with tons of water molecules, magnesium as well, and so you're going to have a very strong propensity for any ionic compound to dissolve in water. Now where that gets a little sticky is when we start talking about how strong the interaction is between the ions in the first place. So if we go back to our solubility tables, which we'll be talking about later in the semester, we have to figure out whether that interaction is actually too strong between these to actually allow water to get in there in the first place. But on a very simple level, in this class, I'd want you to say an ionic compound typically is more water soluble than even something with hydrogen bonding capabilities. So my answer on this one is by far ion-dipole interaction. Yeah?
Can the molecule be, is that capable of hydrogen bonding?
This molecule? Heroin is absolutely capable of hydrogen bonding, yes. And what's really interesting, does this look like a very water-soluble compound?
No.
So this is PCP, angel dust. And what's crazy about it is that you can tell by looking at the structure that it is not very water-soluble. And it's actually so not water-soluble, we call it fat-soluble. If you get PCP on your fingers are mostly lipid layers, and it can go through your skin. And so a lot of people can actually get contact high, like a lot of DEA enforcement agents have to wear gloves because this compound can penetrate through your skin and actually end up in your bloodstream. So some stuff that's applications of polarity that you might not think about on a regular basis. All right, and we've kind of already talked through this, so so let's do one last question on this topic. Which of these opioids would you predict to be the most water soluble? If you're stuck and don't know where to start, please raise your hand. We have lots of people to help.
Because there's only one.
Alright, if you're stuck, please raise your hand.
It's got like a ratio
Oh, yeah.
Yeah, for these have stronger attractions, you know.
I think so.
Okay, has everyone been able to submit an answer? 41 responses. All right, we're closed. I'd like to hear from a new voice to describe some of the process you might be using to think through which one of these would be more water soluble. Aaron? Okay, great. Very good starting point. If you remember from first semester, we had a couple molecules that had more polar bonds, but they also had more nonpolar bonds. And so we have to think about the ratio between polar and nonpolar bonds.
Well, I took that into account because they all have the same base structure.
True, but are there any that in the non-same base structure have nonpolar bonds?
Heroin and codeine both do.
So if we look at heroin, if we look at the whole molecule, we start to notice that this corner and this corner, the two major differences. You guys see that? This one has an O carbon and then an OH, so that's an alcohol, because there's no C double bond or O here. This one has an alcohol, same polarity. What about here? OH, OC. This is an ether. Is this more or less polar than an OH? Less, because it now has a whole bunch of nonpolar bonds, right? 3 nonpolar bonds, CH, 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 and a carbon-oxygen, which is slightly polar, but not as polar as an OH. Right? So in addition to saying how many polar bonds, we want to say how many nonpolar bonds are there, and we want to say how polar are those polar bonds. A CO is much less polar than an OH. So an OH is going to have a much bigger impact on increasing solubility. So then if we look over here, do we think heroin is going to be more or less water soluble than morphine? Why less? Because these two functional groups are not OHs. They're O carbon, carbon, hydrogen, carbon, hydrogen, carbon, hydrogen. And there are 2 CO bonds, but they're not as polar as an OH, and they're masked by, they have some of this. Is there anything else that's different? And then this guy over here, do we have an OH here still? So which one of these do you think is going to be the most water soluble? Morphine. All right. So I want to get you guys thinking about how things dissolve, why they dissolve, and then now we're going to shift gears and start thinking more quantitatively. Maybe you guys already know how to answer this question. It's already been discussed a couple of times. I'm going to give you guys 1 minute instead of 3 minutes. And I want you to say, I think you have this graph printed out, right? On the second page, third page?
Yeah.
Third page. We're on the third page. What would be different, spend 1 minute, what would be different if this is pure water, if we add some salt into that, if we add some solute? What's going to change about this graph? Go ahead and draw in pencil what that difference might look like. All right, let's hear from some new voices. We still have a lot of voices who I haven't heard from, so I'd love to hear from new people. What about this graph would change if we added solute? Aurora?
Everything would just skew left because it would take more of everything to more intermolecular forces to conduct everything, to change the stages, the phases.
Okay, so I love where you're going, thinking about intermolecular forces and how those are changed. They're actually changed in some different ways. So I'm going to have you hold that thought for a minute, and we're going to just think about maybe proposing a slightly different version of what would happen, and then we'll back it into the intermolecular forces and what happened. Kayla?
Would like the heat of vaporization line be shorter since salt would make the water boil faster?
Does salt make the water boil faster?
It's going to increase the temperature at which the water boils, and it's going to decrease the temperature at which water freezes.
Okay, the very simplest things that I wanted you to take out of the homework last night is that colligative properties, when you add solute to the solvent, you both increase the boiling point and decrease the freezing point. That range gets bigger. And I don't want to spend too much time getting into the exact heat capacity. I think it would still be the same, but I'm not 100% on that. What I think is more important to think about is, why does the boiling point go up? Why does the freezing point go down? So I think that's the next question. So go ahead and talk to your neighbor. Answer those next two questions. What question numbers are those?
11 and 12.
Answer questions 11 and 12 with some ideas. And try to remember the very first question I asked. Go back to the very first clicker question, and if your answer has to do with the identity of the solute, it's wrong. It's only based on the number of particles dissolved. That's the real challenge in answering these two questions.
Because that would be like
Not breaking.
Does anyone feel very confident in their answer? That it is not based on the identity of the solute?
Since you're adding more particles to the solution, you have to take away more energy to freeze them, I guess. It's the same with boiling point. If you're adding more particles to the solution, it takes more energy to boil those molecules, or I'm lacking the terminology, but...
So maybe what you're getting at is the line in between phase changes would be longer, or the line during the phase change would be longer or shorter because more heat would have to be added or removed.
Yes.
That is different from why the boiling point goes up. What you're referring to is a left-right shift. What I'm talking about is an up-down. Why does it shift up for the boiling point? So it's not just it requires more heat to heat up more substance to get to the regular boiling point. It's actually that you have to go beyond that. So what does it mean when we warm up a sample? What's happening? What's different about those molecules?
Energy.
Has more energy? How are they moving? Faster or slower? They're moving faster. They have to be going faster on average. So we shift that line to the right in that graph that we drew with the molecules and how much speed you need to overcome intermolecular forces. So what if I said, well, the solute attracts those water molecules. We're talking about water, right? And it has a pull on it, and that pull is stronger than the water-water pull. Why is that wrong? Why is it not about the interaction between the water and the solute? How do we know that's true?
It's only about the number of particles.
The identity is irrelevant. The identity is relevant to see if they dissolve. If they don't dissolve, okay, we're not even having this discussion. But if the things do dissolve, one sodium ion that weighs 23, is that right? 23 grams per mole, has the same influence on changing the boiling point as one antibody from our immune system that weighs 150,000 grams per mole. If that doesn't blow your mind, it should. Literally, the same influence on boiling point will occur for every one particle that's in solution. If we put sodium chloride in solution, how many particles do we have? Sodium chloride. If we put glucose in solution, one glucose, how many particles do we have? One glucose. It's a covalent molecule. It doesn't fall apart, so we have one. That will have the same influence as a sodium ion. All right? So the mental model that I make in my head, a lot of chemistry is this, right? We make models to try to explain things, and if they fit with experimental findings, then they work okay. And the way I've seen it described, I've talked to a lot of people to try to wrap my head around this, because it hurts my head really bad, that an antibody that weighs 100 times as 100,000 times as much as something else will have the same impact. So the way that I look at it, what's the equation for the change in boiling point calculation? Change in the temperature boiling equals
times
We'll come back to this in a second. So the concentration is really important. So if we're looking at a solution and we look at the surface of the solution, there's two things that have to happen for a molecule to become a gas, right? First one is it has to have the right amount of speed to overcome that energy. What's the second thing?
It has to be at the top.
If it's not at the top, it's not going to become a gas. Well, okay, there's extreme cases where you add a ton of heat and you get a bubble of gas from the bottom of the solution. But it has to be going fast enough, and it has to be at the surface. So what if some fraction of the molecules now, where something dissolved, are solute, that can't evaporate, right? Sodium ions can't evaporate. Sugar ions can't evaporate, at least not at these temperatures. What if that molecule was going fast enough that ran into one of our solute particles? That's the best model I've seen. All right, so the higher the concentration is, the more of the molecule, the more of the solution is blocked from those molecules getting up to the surface, means they need to be going faster on average to have more frequent occurrences at the top, going faster to overcome those intermolecular forces. That's the best model I can think of. What about freezing? What's a model for freezing then? What happens when molecules freeze?
The structure gets created, right? Are we talking about water?
Yeah?
Yeah, so it creates like a crystallized structure that is actually very pretty.
It's very pretty.
Yeah.
I agree. So in order for water, when it slows down, to stop moving past each other, you have to cool it down, and then they lock into place. They lock into an extremely organized set of arrangements. What happens if you have solutes in there? They have to be moving even slower to have those intermolecular forces lock into place before they become a solid. So those are the two best models that I've heard as far as why the freezing point goes up and the boiling point goes down. The thing that totally doesn't work in all that is the size of the molecule is also relevant. So that's as far down that discussion as I'm going tonight. All right. So let's spend a little bit of time on factors that influence this change. This is question 13. So go ahead and read question 13. Talk to your neighbor.
Yes, because as you increase, no, that would be wrong. I just want to agree. Yeah, but you have to take it, you also have to take into consideration how much bandwidth factors are being so honestly, yeah.
All right, so we do have a little bit of a mix of answers, but one of them stands out. So we have the most votes for answer C. Would anyone like to describe why they answered C? Can I get someone from that back corner? Humphrey? Okay, why did you pick A? And I might have actually said that backwards. Did I say that backwards? I did say that backwards. A has the most answers. Okay? I love your confidence, by the way. You're like, you know what, screw the class. I'm going to go my own way. Alright, so you said that you think solution 1 would have the lowest freezing point because you said it has... Why? Fantastic. How many particles will we make for every NaCl? And every ethanol? 1. That's referred to as the Van Hoff factor, the theoretical Van Hoff factor. All right, and so what if I told you, so as this question is worded right now, how many moles of particles do we have for solution 1? 0.75 moles of particles. Remember I said we'll get to this in a second? The change in the temperature, boiling or freezing, both of them have this I in the equation if you use the right equation. So that means this would be the concentration in molality, and we'd have to figure that out based on density here. And then you say, well, this is for calcium chloride, and then it has a Van Hoff factor of 3, so it would have 3 times the impact on the change in boiling point or freezing point based on that property of its. What if I told you that if we change the scenario and I said, well, actually, this one isn't soluble, would it still be the correct answer? Then you would have, this guy would be, so in 1 has to dissolve, and in 2, then it's how many particles, how many moles of particles, or the greatest concentration of particles in solution. I think the next question we kind of already answered, right? So you can go ahead and write out your definition for Van Hoff factor on your own. We only have 3 minutes left of class. So I wanted to focus on the difference. This isn't in your worksheet, and you might use this to describe your definition. What's the theoretical Van Hoff factor for sodium phosphate? We want to make sure to recognize our polyatomic ions. Phosphate is 1 ion, 3 sodiums. So our theoretical Van Hoff factor is 4. But something we talked about earlier, sometimes the attraction between the different components of a salt is stronger than the benefit gained energetically by having water introduced. So what we actually find, the theoretical is 4, but when we actually measure it, we only find the equivalent of 3.1 particles for every sodium phosphate are released. Potassium sulfate, it's 3 compared to 2.3. Calcium chloride is less again. Magnesium sulfate, does that mean it's very soluble? You almost only get 1 particle for every 1 magnesium sulfate. So my earlier question probably was not the best, because I use magnesium sulfate compared to heroin. Sodium chloride, however, is very soluble. And what is the Van Hoff factor for ethanol? Molecular compound. All right. We still have 2 minutes. We're not going off that clock. It's wrong. Okay. Yeah, that's what I got. All right. So let's do a calculation.
Right?
What information do you need to answer this question? You can Google the molar mass of ethylene glycol. These are the 2 equations that we're going to be using. And some constants that might be useful.
We need the math. Did you find it? 16.
Was it using ionic compounds? Or molecular? Go back to those. All right. So we're just about out of time. Which of those 2 equations are we going to use? We're looking at the change in freezing temperature. Is this constant the same for every single molecule? Why? What would be different between different molecules? Intermolecular forces. So that is related to the intermolecular force strength. So this says that in order to change the freezing temperature of water by 1.86 degrees Celsius, we would need a 1 mole solution. If we had a 2 mole solution, we're going to change the freezing point by 3.672 degrees Celsius. Changing it by a certain amount doesn't mean positive or negative. It will decrease. So if we're to calculate this one here, how do we find molality?
Is it degree per Celsius per mole or per mole out?
How many moles of solute do we have?
I did too. That's what I got.
3.62 is a mole concentration?
Yeah.
Okay.
No, that was molality.
And how many kilograms?
It's 1,000.
No, that is the molality.
Yeah, she did.
Oh, it's the molality.
Yeah, she did the whole thing. And I was like,
Yeah, that 3.62 is the molality.
because it's actually 6.
So what's our Van Hoff factor? 1, it's a molecular compound. What's our KF? So what do we get for delta TF? Or delta, yeah, TF. What'd you get? 6.17. All right, is this the right answer?
No.
I got 7.3.
Why?
You have to subtract it from the freezing point.
So the really important thing is that we don't say whether it goes up or down, right? It's just the change, and we have to know the freezing point goes down. What's the original freezing point of water?
0.
So it's 0 minus the change is our final freezing point. So molality, I didn't find the number of moles. Someone just told me this is how with the molality of the solution. The molality means this is the ratio. I didn't calculate that. Is that the number of moles, or this is the ratio per kilogram? What's the molality of the solution?
That number right there.
Molality is defined as the moles of solute per kilogram of solvent, correct? So if you find the number of moles of ethylene glycol, you divide it by that many kilograms of the solvent, you should find 3.62 mole. I decompress molal into that. All right, I'm happy to stay for class and talk. Thank you guys for letting me go over a little bit, a lot. Don't forget a supplemental instruction sheet if you didn't grab one, and a periodic table card if you don't have one yet.
Look at you. You people.
I thought in the book it said